Hello students, on behalf of United Group of Institutions, I Swarup Malik welcome you all to this online class of Basic Electrical Engineering. Today I am going to take lecture number 6. Today's topics are Autotransformer and Three-phase transformer connection. So the first question that arises in our mind is that what do we understand by autotransformer? So this is the first question that will arise in your mind, and you all have already seen this autotransformer in your basic electrical engineering lab. This is the image of an autotransformer. You have used this autotransformer while you have determining the slip of a three-phase induction motor. You have also used this autotransformer while doing other electrical practicals. This is basically responsible for giving variable voltage. So this is basically the image of an autotransformer, and from this autotransformer we are actually getting variable voltage below 230 volt. So this is the internal structure of this autotransformer. Here we have a single, you can say, a winding. Only single winding is there in this autotransformer. So let us start today's lecture from autotransformer. I have planned my today's lecture in these topics. First, what is an autotransformer? Second, autotransformer theory. Third, copper savings in autotransformer. Then advantages of using autotransformer. Disadvantages of autotransformer. Applications of autotransformer, and followed by our last topic, three-phase transformer connections. So let us start with what do we understand by autotransformer. So you can see from this video that an autotransformer is a kind of electrical transformer which only contains one winding. That is, we have only one common winding, and from that winding we are actually defining the primary and secondary side by defining it from a point we call it as a tapping. So through a tapping we can distinguish between a primary side and a secondary side, as compared to a traditional transformer where we have two different windings for primary and secondary side. But in autotransformer we have only a single winding. So let us start the theory of autotransformer. So in an autotransformer, one single winding is used as primary winding as well as for secondary winding, as compared to two winding transformer. So here we have a circuit diagram of autotransformer. You can see from here we have only just a single winding. So here this is a case of a step down autotransformer where AB is the primary number of turns. We call it as N1. So from A to B we have N1 number of turns. We have a tapping in between A and B, and we call this point as C. So this BC is our secondary winding, and let us assume that the number of turns from B to C will be N2. Okay, this part BC will be common to primary side as well as to secondary side, and let us assume that the number of turns in this BC is N2. So and the number of turns from A to B is N1. So what will be the number of turns from A to C? It will be N1 minus N2. Okay, so we have applying a voltage V1 at the primary side, and when we connecting a load in secondary side, the voltage V2 will be produced across this load, and a current I2 will starts flowing in this load. So when this I2 will flow back to this winding, what happens? I1 will be returned to the primary side, and a current I2 minus I1 will be flowing through this winding BC. Okay, so from A to C we have a current I1, we call it as a primary current, and in the winding BC we have a current which is equal to I2 minus I1. Okay, so this is a brief introduction of auto transformer, and all this technicality that I have make you understood through this image has been written here. So we can say that if there are n1 number of turns in this primary side, and we have a total applied voltage in the primary side is V1, then what will be the voltage per turn? Voltage per turn means what will be the voltage in an individual turn of a transformer. So the voltage per turn will be equals to total voltage divided by total number of turns. So it will be V1 upon N1 in the primary side. So here it is written. So voltage per turn in the winding, that is in the primary side, will be V1 upon N1. Similarly, if we want to determine the voltage per turn in this secondary side, that is in BC, then what will be the formula? Yeah, we know that the number of turns is this will be from C to B, it will be n2 number of turns. So we will multiply V1 upon N1, that is voltage per turn, into number of turns in the secondary side, that is N2. So what will be the voltage in the secondary side? It will be V1 upon N1 into N2. You can see from here voltage per turn in the winding is V1 upon N1. Hence the voltage across the portion BC of the winding will be V1 upon N1 into N2, and it must be equal to V2, because we know that in the winding BC the voltage across it is N2. So V1 upon N1 into N2 will be equals to V2. So from here we are getting V2 upon V1 is equals to N2 upon N1, and this is a constant term. We call it capital K, that is turns ratio. Okay, so K we have already obtained it for two winding transformer, and there also we have seen that V2 upon V1 is equals to N2 upon N1. So it will remain the same for auto transformer also. And let us talk about this copper savings in auto transformer. Since you have already seen that in a normal traditional transformer we have two windings, but here we have only one winding. So we can see here that in an auto transformer a saving of conductor material is possible, because in a traditional two winding transformer we have a copper conductor in primary side as well as copper conductor in the secondary side, but in auto transformer we have just a single winding. So the copper conductor for secondary winding has been saved. So in this way, while we are manufacturing an auto transformer, we are actually saving the copper material, having the same rating. So how is it possible? Let us go through it. As we know that the weight of a conductor is depends upon two things: the length of the conductor as well as the cross sectional area of a conductor. The length of a conductor can be directly proportional to the number of turns in an auto transformer or in any transformer, because as we increasing the number of turns in a winding, what happen, the length of the transformer will of the conductor will increase, thereby increasing the weight of the conductor. Similarly, if we increasing the cross sectional area of a conductor, then cross sectional area will be directly proportional to the current. More will be the cross sectional area, more will be the current. So we can say that the weight of a conductor will depends upon two things. One is length of the conductor and second is area of cross section. Length of the conductor can be directly proportional to number of turns, and the area of cross section of a conductor is also directly proportional to the current through the conductor. So in this way we can say that weight of weight of copper in section AC is proportional to N1 minus N2 into I1. So how is it possible? If you see the part AC, then you can see from here that in the part AC how many turns are there. It will be N1 minus N2, because here we have N1 turns from A to B, and from B to C we have N2 number of turns. So how many turns are there in this part AC? We have N1 minus N2. And what will be the current through this part? It will be I1. So the weight will be directly proportional to N1 minus N2 into I1. N1 minus N2 into I1. Similarly, in the BC part, what will be the number of turns? In this BC part, we have number of turns as N2. And what will be the current? It will be I2 minus I1. Here we have I2 minus I1, that will be the current. So in this way, if we consider the whole winding, so the total weight of the copper conductor will be this much plus this much, because if you consider the whole winding, then the whole winding will be from A to B. So it is a combination of AC plus BC. You can see from this image, from A to B it is a combination of AC plus BC. So it will be your this part plus this part. So this is the total weight of the copper in the winding of autotransformer. So now when we simplifying it, you can find it as 2 times N1I1 minus N2I1. Okay. So if you take a 2 winding transformer, then in the primary side what will be the weight of the conductor? It will be N1I1. And what will be the weight in the secondary side? It will be N2I2. Since we know that in a transformer N1I1 is equals to N2I2, so therefore we replace N2I2 as N1I1. So what we are getting? We are getting 2 times N1I1. This relationship also holds true in autotransformer. You can see from here. Here we have written N1I1 plus N2I2 minus 2 times N2I1. But since N1I1 is equals to N2I2, so we are replacing N2I2 as N1I1. So that's why we are getting here 2 times N1I1 minus 2 times N2I1. We are getting common from these two parts. So we are getting this much value. And when we are taking a 2 winding transformer, so the total weight of the conductor is proportional to 2 times N1I1. So if you assume that the weight of the total conductor in an auto transformer is WA, and in a 2 winding transformer is W with suffix TW, so what will be the ratio between WA and WTW? It will be equals to this much. This is the weight in the auto transformer side, and this is the weight in the 2 winding side. So what we are getting? We are getting this much, that will be equals to 1 minus N2I1 upon N1I1. I1 will get cancelled out, so it will become 1 minus N2 upon N1. So it will become 1 minus K. So we can say that WA, that is weight of conductor of auto transformer, will be equal to WTW, that is weight of the two winding transformer, minus K times WTW, where K is the turns ratio. So in this way we can say that while we are manufacturing an auto transformer having same rating as of a two winding transformer, we are actually saving the copper material. And how much we have saving? We are saving this much. Okay, so it can also be written here that therefore saving of copper in auto transformer compared to two winding transformer is WTW minus WA, that is the saving in the conductor material. It will be K times WTW. Okay, so this much copper material we are saving if we manufacture an auto transformer. So now we see the advantages of using auto transformer. So advantages is very simple. Since the weight of the conductor is less as compared to two winding transformer, so it will be cheaper, the cost will be less as compared to a two winding transformer. Second, it has higher efficiency as compared to two winding transformer, because in two winding transformer actually there is no electrical connection in between the two windings, but in auto transformer the actually the power is also transmitted through the electrical conduction. So power is not only transferring through your mutual inductance but also through conduction. So that's why losses will be decreased as compared to two winding transformer, because there we have two different windings. So copper loss is also present in primary side as well as in secondary side, but here we have only copper lost in a single winding only. So efficiency will be more as compared to two winding transformer, and auto transformer has better voltage regulation as voltage drop in resistance and reactance of the single winding is less. So obviously its voltage regulation will be less as compared to two winding transformer. So these are few advantages of auto transformer. Let us discuss about the disadvantages. The disadvantage is that there is a electrical conductivity between primary and secondary side. As a result of that, in the secondary side, it becomes necessary to design the low voltage side circuit to withstand higher voltage. Actually what happens, we have to take extra precautions in the secondary side of an auto transformer, because what happens that there is a conducting path between primary and secondary side. So extra precautions should be taken so that we are able to withstand higher voltages in the secondary side. Second, the leakage flux between the primary and secondary windings is very small, and hence the impedance is very low. So severe short circuit currents under fault conditions can occur. Since we have a very less amount of impedance, so more current can be flow through it under faulty condition. So if a fault occurs, then the whole winding of the transformer will burn out due to severeness of current. Okay, and third point, it is more difficult to maintain the electromagnetic balance of the winding when voltage adjustment tappings are provided. It should be known that the provision of tapping on an auto transformer increases considerably the frame size of the transformer, and thereby also increasing the initial cost of the transformer. So less tappings should be used so that the cost should be less, and a maintenance of electromagnetic balance should be possible. Okay, applications of auto transformer. So compensating voltage drops by boosting supply voltage in distribution system. You must have seen the boost up transformer in our distribution system to compensate the loss through the wires. of the supply system. So for boosting purpose, auto transformer with a number of tappings are used for starting induction motor and synchronous motors. Auto transformer is used as variac in laboratory or where continuous variable over broad ranges are required, that I have already discussed with you, that we are using extensively this variac in our electrical labs for getting variable voltages. So these are the few applications of auto transformer. The three-phase transformer connections is our last topic. So actually what happens that in a three-phase transformer, the primary as well as secondary sides are having three phases. Okay, since we have seen the single phase transformer where we have one primary winding and one secondary winding, similarly in three phase transformers we have three primary windings as well as three secondary windings. Now the question arises that how the three windings are connected in a side, whether it is primary side or it will be a secondary side. So let us discuss about it. So as we all know that there are two types of connections possible for a transformer. One is star connection, another one is delta connection. Okay, in star connection what happens, we suppose this is a one coil of a winding, this is another coil of a winding, and this is another winding. So we have three windings and we have three voltage phases connected to these windings. So these windings have one ends where we are supplying the voltage and the other ends have been connected together. This is called star connection. But in delta connection, you are seeing in this image that what happens in delta connection, that from one side we are applying a voltage in a coil and other side of the coil is connected to the beginning of the another coil. Similarly in coil number 2, this second side, that is the other side of the coil, is connected to the first end of the third coil. So in this way we are connecting a delta connection and here we have a star connection. Suppose in this connection, suppose this is a winding, we call this side as A and we call this side as A dash. Similarly in this coil we call this side as B and we call this side as B dash. Similarly in this coil we call it this side as C and this side as C dash. Then you can see from this diagram that A dash, B dash and C dash, all three are connected together to form a star connection. Okay, but this is not in delta connection. Suppose this is A and this is A dash, this is B and this is B dash, this is C and this is C dash. So you see from this diagram that A dash is connected not with B dash but with B. Similarly B dash is not connected to C dash, this is connected with C, and similarly C dash is connected with A. So here we are getting a delta shape and here we are getting a star connected shape. Okay, so here this same kind of polarities are connected together and here different types of polarities are connected together. So here we have the types of three-phase connections. First we are discussing star-star connection. So this is basically a star-star connection. You can see from this diagram, this is the primary side and this is the secondary side. In primary side we have three windings and also in secondary side we have three windings. So if you see here that as this is A, we call this end as A dash, this is B, we call this end as B dash, This is C and we call this end as C dash. So A dash, B dash and C dash, all these similar ends has been connected together and they have been grounded with the neutral. Similarly, in the secondary side, these similar coils, the similar ends of the coils has been connected together to form a delta connection. Okay, then we star connection, that was the star connection. Okay, this is a star connection. Okay, so here we have a delta connection. You can see from here that here we have a delta connection that I have already discussed, and here also we have a delta connection. So what happens in delta connection? In delta connection, the other end of the coil is connected with the first end of the coil, of the second coil. Okay, the other end of the first coil is connected with first end of the second coil. Similarly, the other end of the second coil is connected with first end of the third coil. Okay, and the other end of the third coil is connected with first end of the first coil. So this, in this way we are getting a closed connecting supply. So this is our delta connection. So basically star connections are used, were generally used for small high voltage transformers, and delta connections are used for large low voltage transformers. Okay, then we have star delta connection. So what happens in star delta connection? We have a mixing up of primary and secondary side. In primary side we have a star connection, and in secondary side we have a delta connection. We are using this transformer as a step down transformer at the substation end of transmission line, and here the primary side will be in star connection and the secondary side is in delta connection. Similarly, we have also a delta star connection, where we have a delta connection in primary side and star connection in secondary side. This is used for step up purpose in our transmission line. So these are the four primary connection types of three-phase transformer connections. This is the combined image of all the four, so that you can easily distinguish between all these four images. You can be able to understand as well as differentiate each other, that how they are differ from each other. So these are the four primary types of three-phase transformer connections. So there are two more types. We call it as open delta connection, that is your VV connection, where we have only two coils in the primary as well in secondary side. So we call it as VV connection. And there we also have a Scott connection, we call it as a TT connection, where there we have a main winding transformer as well as a teaser transformer. So you can go through it. That's all. Thank you. Have a nice day.